Hello everyone, this is Dr. Lennon and we are looking at surface area today. So again, you can see this is kind of another formula that bears some resemblance to the arc length formula, but we've got some extra factors in front. So this formula pretty much works for all of these, similar to the shell method when you're looking at the volumes of these objects that you're revolving, these two-dimensional graphs, but this is the surface area. So we have a non-negative function with a continuous first derivative on some closed interval, and then the area of the surface area generated when the graph is revolved around the x-axis is given by the following formula. Again, as with surface areas and everything else, we can make analogous formulas when we want to solve for y rather than x. But we have the integral over that interval from a to b, and it's 2 pi times the function times the square root of 1 plus the derivative of the function squared. Once again, these things can be quite messy just because we have the square root and a complicated quantity involved. So in practice, you may end up doing a lot of these using numerical techniques, but we'll look at a few that we can do by hand and maybe on your homework. So let's go ahead and start with the first example. Okay, so we're looking at this graph 2 square root of x on the interval 1, 3, rotated about the x-axis. Again, if you want to think about the picture here, it's not too difficult to envision. We know 2 square root of x is going to look roughly something like this. So we're rotating a section of it about the x-axis. We're getting kind of this this part of this kind of reverse kind of cone. So we've got that section here, which is, again, this is just a two-dimensional image of what we're doing, but you get the idea. So we're trying to find the surface area of that kind of bowl with an open top and open bottom. So according to the formula, we also need to know the derivative. So f prime of x, we know, is just going to be x to the negative 1/2, or 1 over the square root of x, because the 1/2 from the power is going to be canceling with the 2. So our surface area here is going to be the integral from 1 to 3 of 2 pi times our f of x, which is 2 square root of x, times the square root of 1 plus our f prime of x quantity squared. This one's going to work out quite nicely, but you can imagine these things can turn into quite a mess. So we have the integral from 1 to 3. Let me pull the 4 pi out front just to make it a little more organized. So I'm going to write the 4 pi in front. And then what do we have left on the inside? Well, we have a square root of x, and we have the other square root that is being multiplied by. That's going to be 1 plus just 1 over x. So we can actually combine those by multiplying inside the square root, and if you distribute the x through, you're going to get x plus 1. So this is actually just 4 pi integral from 1 to 3 of the square root of x plus 1 dx. Remember, if you have the square root of a times the square root of b, that's the same as the square root of ab, so that's not a problem there. And that's something that we know how to integrate. There's no chain rule to worry about because u would be x plus 1, so du would equal dx. So this can just be written as 4 pi times, well, we're going to have 3/2 as our new exponent, so we're going to need a 2/3 in front. And then we have x plus 1 to the 3 over 2. And this needs to be evaluated from 1 to 3. So let's go ahead and do that. So we get 4 pi times 2/3. And then we're going to get 4 to the 3 over 2 minus 2 to the 3 over 2, 1 plus 1 for the second one. And apparently that comes out to 16 pi over 3 times 4 minus the square root of 2. So can we see that pretty easily? Well, we know when you do yeah, so we're going to end up getting essentially inside the parentheses 4 to the 3 over 2 is going to be 8, and then minus 2 to the 3 over 2 is 2 radical 2. So we have an extra factor of 2 that we can pull out, and that's why we're left with 16 pi over 3 times quantity 4 minus the square root of 2. So yeah, pretty straightforward there, but you can tell the formula is even more complicated typically than the arc length formula, so these things may not come out so nice. Anyway, let me go ahead and pause the video and get another example started up, and then we'll go ahead and get back to it. Okay, so here's another relatively simple one. We're trying to find the surface area of a frustum of a cone. That's right, so a cone just, kind of looks like a dunce hat or something like that. Basically, what happens here is we have y equals 2x, which is, something like this. And we're rotating it, but we're cutting off the top since we're starting at 1 and going to 6. So we're getting the part of the cone that starts at this first circle and goes to the bottom circle. So we're just getting this section of the cone. We're cutting off kind of like the pointy end at the top. So again, f prime of x here is going to be very simple. It's just going to be 2. So in cases like this, the surface area integral is going to be very reasonable because that'll just be a constant, whatever we're taking the square root of. Okay, so we should be taking the square root from, or the integral from 1 to 6 of 2 pi times f of x, which in this case is 2x, times the square root of 1 plus f prime squared. So 1 plus 2 squared, so 1 plus 4 dx. So again, this is much easier to compute. Everything's really a constant. So we can pull the 4 pi and the square root of 5 all out front. 4 pi times the square root of 5, integral from 1 to 6 of x dx, and the integral is very simple. We're just going to get x squared over 2. I'm going to bring the 2 out front and divide that into 4. So I have 2 pi square root of 5 x squared from 1 to 6. So we multiply 2 pi square root of 5 by 6 squared minus 1 squared, which is 35. So that gives us our final answer of 70 pi times the square root of 5. And if we do that in our calculator, just to get an idea, we end up with 491.7 units, something like that. Oh, units squared, actually. So that's the other thing I wanted to remember to say. When we're dealing with these surface areas, remember they are going to be units squared because they're actually areas around the outside. So when you talk about like a length, that's a single unit measure. Areas are going to be squared unit measure, and volumes are going to be cubed unit measure. Okay, so let's do 1 or 2 more examples, and then that'll be it for this section. Okay, so let's go ahead and look at this example. So we have the curve f of x equals the square root of minus x squared plus 12x minus 20 from x equals 3 to x equals 5 is rotated about the x-axis. So it looks like a big mess right now, but it's actually going to come out much simpler just due to how the derivative works. So again, this derivative can be found using the chain rule. So if we do f prime of x, what is that going to be? Well, basically, we're going to have a 1/2. We're going to multiply by the derivative of the inside, which is going to be minus 2x plus 12. And then we're also going to be multiplying by the same quantity to the negative 1/2 power now. So that's going to be 1 over the square root of minus x squared plus 12x minus 20. So this can be rewritten as minus x plus 6 over the square root of minus x squared plus 12x minus 20. And so that square root that we see down here is actually going to cancel with the f of x that we have when we're doing the surface area. So that's going to make things a little bit easier, even though right now they look complicated. So the surface area formula is given by, well, we have 2 pi, we have our integral, which I believe 3 to 5 is what I said. Yeah, 3 to 5. And then what we're doing is we're multiplying by our function, which is the square root of the minus x squared plus 12x minus 20, and then we're multiplying by the square root of 1 plus this quantity that this f prime of x squared. So we have minus x plus 6 over the square root of x squared minus x squared plus 12x minus 20. So it looks like a gigantic mess, but we're going to get some nice cancellation eventually. Okay, so how is that going to happen? Well, let's just think about what's going on with our second term there. So let's just rewrite what's going to stay the same. So we're still going to have our 2 pi. We're integrating from 3 to 5. And then we've got this square root that is going to go away soon. But for now, we're just going to keep. So how is it going to go away? Well, we can get a common denominator, in fact, with 1, right? We can write 1. So how can we think of this? Well, is there an easy way to put it? Well, sure. When you square this term, we're going to get minus x plus 6 quantity squared. And on bottom, we're just going to get this minus x squared plus 12x minus 20. Well, we can write 1 as that. So what I'm really doing here is I'm writing minus x squared plus 12x minus 20 over minus x squared plus 12x minus 20. That's my clever form of 1. That's how I'm rewriting 1. And then I'm going to have minus x plus 6 quantity squared over this new denominator of minus x squared plus 12x minus 20. And that's going to allow me to combine them into a single expression. And actually, if you notice, what is minus x plus 6 quantity squared? It's going to be x squared minus 12x plus 36. So in fact, the top, when you add those two terms, you're just going to end up with 16, if you can believe it. So I'll leave that for you to check. But if you FOIL out the minus x plus 6 quantity squared and then add that with the other term that we are getting a common denominator for, you'll just get 16. So what this will end up being is 2 pi times the integral from 3 to 5 of this square root of minus x squared plus 12x minus 20. And then what we're going to have over here is the square root of 16 over minus x squared plus 12x minus 20. And we can rewrite that using the square root of the top and the square root of the bottom, and that's where we'll get that big cancellation coming from. So we'll have 2 pi integral from 3 to 5. We'll have this square root minus x squared plus 12x minus 20. And in the second factor, we'll have the square root of 16 over this square root of minus x squared plus 12x minus 20. And so this term cancels, or that factor cancels with that factor. So that's all we have is the integral of 4, which we can write as 4x, doing the antiderivative. So if we take the 4 out, what do we have left over? We have 8 pi with our x, and we're integrating from 3 to 5. So in fact, this is just going to turn out to be 40 pi minus 24 pi, which is 16 pi. And that is it for the surface area. Again, if we had units, we would write whatever those units are squared. Okay, so that one was a bit messier, but again, it worked out in the end. So I think that's about as complicated as the ones that you'll see. In general, these are computationally pretty intensive, so oftentimes you'll just appeal to numerical methods. But you can see how some of these things work, and you can prove where some of the formulas from geometry that you've encountered in the past will come from when it comes to these surface areas. So that's it for this section. Again, very similar in terms of the arc length section. The formulas are kind of similar. They're computationally difficult, but you just kind of plug things in and do algebra till everything simplifies. All right, this is Dr. Lennon signing off.